Okay, so for your lab that we're going to do, you're going to be calculating the actual kinetic energy that different bodies possess. We'll be throwing objects and we'll be running up the stairs too. So in order to calculate that exactly, we have a refresher video here that steps you through the equation for kinetic energy. But just first to review, what is energy? Energy is defined as the capacity to do work, any kind of work. It's what makes things go in a certain way. There's two different kinds of energy. So the energy that makes you go is kinetic energy. And that's just defined as the energy that a body possesses by virtue of being in motion. So a baseball, when it's thrown, has kinetic energy. When it interacts with another body, it has the potential to change that object. If it hit, you can think of it, pool balls would be maybe a better example. When you hit the cue ball, it has kinetic energy and it can transfer that to another object. And then those objects are in motion. Potential energy comes in a variety of different forms. If a rock is perched high up on a cliff, we say it has high potential energy. But a rock that is perched on an even higher cliff, we say has even more potential energy. Some objects have stresses stored within themselves. Elastic objects, springs, they have that kind of potential energy. Watches and things like that run off of potential energy. Electric charge is another example. A battery has potential energy. It's not necessarily using its potential energy at all times, but it can. And there can be other factors with potential energy as well. So the standard way that we measure energy is with joules. And a joule is defined as the energy necessary to push a 1 kilogram mass a distance of 1 meter in exactly 1 second. So if you were trying to push an object, it takes more energy to push the object fast versus slow, right? So the joule has to be super specific. It's exactly a 1 kilogram mass. You push it exactly 1 meter in exactly 1 second. Now, depending on the person or the machine or the object, the object may have to exert more of its potential. It may have to try harder to push a mass that distance in that second. But in either case, the exact same amount of energy is being used to accomplish that. We also have the watt, which is 1 joule per second. It's essentially the exact same thing as the joule. A kilowatt hour is the way electricity consumption is measured. So these are going to be the most common units we see when it comes to energy around us. There are also BTUs and calories and many other things. But 1 kilowatt hour would keep a 100-watt light bulb lit for 10 hours, which is the equivalent of over 3.5 million joules or 3.6 megajoules. So a single joule is really not very much energy, as you can see. And with these units, it's important to keep this in mind because when you calculate things, your decimals may be moving over, or you might have to convert before you get to a certain point. You cannot calculate two things, one that's kilo and another that is mega, side by side. You would have to move the decimal points around before you do anything, or your answers are going to be completely wrong. So kilo is 1,000, mega is 1,000,000, giga is a billion, and tera is 1 trillion. We will pretty much be using kilo, mega, and very rarely giga. So we're going to do an actual problem here. This is the formula for calculating kinetic energy. You take 1/2 times the mass of the object times the velocity squared. Now your mass has to always be in kilograms. Don't do it in grams. Don't do it in tons. Always kilograms. And you cannot do it in pounds either. It absolutely has to be kilograms. And you absolutely can only multiply kilograms by meters per second. These are both SI units. If you try to do pounds and miles per hour, it will not work at all. It just simply won't work. So we're going to, knowing this, we're going to take a Major League fastball, which is measured in miles per hour, and we're going to calculate how many joules that object has. So our first step is to convert miles per hour into meters per second. So we have 100 miles over 1 hour. Now, what we're going to do first is convert our distances, and then we'll do time. So we're going to go from miles to meters. Well, how do we do that? Well, we will take how many kilometers, first of all, there are in a mile. So 1 kilometer is not quite a mile. It's about 2/3 of a mile. So there we go. Now, if we look here, and I'm going to change my screen. Let's get rid of that. If we look here, we are going to be canceling things out as we go. So miles over here cancels out with miles over here. So we're left with just kilometers and hours. Oh, it won't let me switch. Okay, well, I guess we're going to do it this way. So next, we need to take kilometers into meters. So there are 1,000 meters in 1 kilometer. Now, if you look here, our kilometers cross out. So we're left with just hours and meters so far. So we've got it down to meters, but we need to have seconds. So how many seconds are in an hour? It's 3,600, but the easy way is to do 60 minutes in an hour first. So now you can see our 1 hour at the beginning is canceled out with our hour over here. So we're left with just meters and minutes, but we don't want minutes, we want seconds. So 60 seconds in a minute. So our minute just canceled out. Now we've narrowed it down now to meters, where we have 1,000 meters, and seconds, where we have 60 seconds. There's nothing left to cancel those out. So if we multiply these numbers here, 100 times 1 is 100, times 1,000 is 1,000, times 1, or is 10,000, I'm sorry, times 1 times 1. And then on the bottom, we end up with, I can't do that in my head, but it's 2,235.6. So the velocity of the baseball is 44.731 meters per second. Good. Now it's in a form we can actually use. The mass of a baseball, I wouldn't expect you to know that, but it's 145 grams. Now, again, we have to have that in kilograms. How many grams are in a kilogram? Kilo means 1,000. Divide it by 1,000, or just move our decimal point 3 places to the left. So it's 0.145 kilograms. So we plug this into our formula. 1/2, or 0.5, times the mass of the object, times the velocity squared. So I want you to actually calculate this really quick here. Okay, here is the answer you should have got, 145.06 joules. Now, if you got 10.517 joules, you did not follow your order of operations correctly. Remember, we have, please excuse my dear Aunt Sally, right? Parentheses are first. Well, we don't have any parentheses. So next is exponents. You have to, and this is why I put everything in brackets, you have to take 44.731 squared as the very first step. Okay, you cannot do this equation left to right. If you do it left to right, you get 10.517. That's not the correct answer. So you have to square 44.731 first, and then you can multiply either of those numbers first. It doesn't even matter after that point. But that is how we get our answer here.